All right, good morning everyone, and welcome back to the last lecture for MSD 780. This is also the last lecture that we're going to focus on optimization and its integration into the DAP-BC workbench. So before I jump in, just a few logistics. So we're going to work with the DAP-BC Dynamic Queue Revision 1 workbench today. The example that I'm going to show is going to be directly in the Octave DAP-BC Dynamic Queue workbench. So you're more than welcome to download that while we're busy over here. And then also, I did receive a few requests with regards to the first lecture on this optimization that we did, just to have that available as a lecture video as well. So that should be posted by next week, Thursday, which would have been the last lecture, but today is now the last in-person lecture. So you should have all the lecture videos available by next week, Thursday. Right, so before we jump in with today's application example, I just quickly want to go through what we said in the previous two lectures. So just looking at the introduction again, we mentioned that the DAP-BC workbench, being a numerical approach, can be integrated with other optimization workbenches and other optimization or other workbenches in general. We're not limited by the user interface, so we can expand quite a lot with regards to the standalone DAP-BC workbench. And one of those that we looked at was the dynamic queue optimization. Just to show you the general form again, our dynamic queue optimizer minimizes some sort of an objective function subject to a set of inequality and equality constraints. And then we also have the lower and upper bounds that we can define on each of the variables. And then, of course, this last line, which is our move limit, which is simply determined by our maximum variable range that we're working with. So we're going to look at an example today of how this move limit actually influences the optimization convergence behavior. So just moving on then to the optimization only examples, I did give a general procedure over here as well. So this was an addendum to the dynamic queue optimizer that was produced by Dr. Alex Hay back in 2002. And over there, we looked at 3 example problems, all of them having known analytical equations and known analytical constraints as well. So the results that we got, we could validate from an analytical perspective. However, we saw that with the DAP-BC workbench, we know that it is an iterative process that it uses. It uses like the ODE 45 integration scheme within Octave to basically perform either forward or inverse dynamics. So we can't rely on any analytical equations to really validate our results. Instead, we use something like a dynamic queue optimizer to now check what our maximum or minimum objective function is going to be. So with regards to that, we also looked at a general optimization procedure. So the first procedure over here, which consisted of around 4 steps, is basically just setting up the DAP-BC workbench so it can be integrated with dynamic queue, so that we don't have to give it any inputs. We sort of optimize or automate the process that we're using over there. And once that is done, we can then move on to the 10-step procedure, which we use to essentially execute our optimization study and to see what the optimum solution is going to be at the end. So with regards to that, we then moved on to the application examples, and we first looked at the driven pendulum subjected to a constant torque. And we said there were 4 design variables that we considered. So that was the mass of the pendulum, pendulum rod, the length of the pendulum rod, as well as the starting angle, and I believe the other one was the input torque that we also gave it. So we wanted to measure the kinematics or the acceleration and the speed of the torque or the pendulum rod after, I think it was 3 seconds that we used over there. And we saw that the optimization converged quite well over there. So we did get a maximized acceleration, and the speed was also in accordance with the equality constraint that we provided over there. Right, so for today's example, we're going to focus on a card subjected to an aerodynamic and a torque load. So if you recall correctly, this is card D that you looked at in lecture 8. So this is just a general schematic once again of the cart, just showing that we have three bodies. So we have the cart body denoted as body 1, and then we have the two wheels, the rear wheel and the front wheel, which are denoted by bodies 2 and 3 respectively. So then we can also look at the assembled cart, and we could obtain the center of mass locations over there that we needed to define under in bodies. Right, so with that being said, we also defined a forward dynamics problem. In other words, we proposed some sort of a relation for the motor torque based on a maximum allowable torque, and we measured the angular characteristics of the wheels in the cart body, so the speed, the acceleration, angular speed, angular acceleration, all of those kind of things. Right, so a few of the results that we got out over there, we can see that the velocity of the cart over here is shown, and we got around, I think it was 1.25 meters per second out over here. So the dotted line or the dashed line over here is just basically when you have some sort of aerodynamic force acting, and over here the solid line is for no resistive force that was applied. And then we could also look at the angular characteristics, so the angular speed of the wheels. As we can see over here, it's negative, which corresponds to the fact that the cart is moving from left to right, so we expect the wheels to rotate clockwise. Right, so sticking with the forward dynamics problem, we can now ask ourselves a few design questions. In general, we're going to ask two questions for this example, and that relates to how the maximum torque that we specify is going to influence the acceleration of our body, and what is the influence of the aerodynamic drag coefficient on the speed of the cart. So two very simple design questions that we can then use to formulate our design problem. So in general, what we can say is we want to maximize the acceleration of the cart body subject to the maximum torque applied to the rear wheel and the aerodynamic drag coefficient. So once again, if we analyze this statement, we want to maximize the acceleration. So the acceleration of cart body 1 is going to be our objective function, and it is subject to two design variables, which is now the maximum torque, or the torque applied on the rear wheel, and also the aerodynamic drag coefficient, which is our second design variable. Right, so just considering a few design parameters as well. So these are just in addition to what we specified. This is user specified. So we can say that the maximum time that the motion should occur over is 6 seconds, and we want to use a reporting time step of 0.1 second. So we get around 60 time steps that we can use for analysis. So basically 60 points along our motion that we're going to analyze. And then the torque should not exceed 50 Newton meters as well, so this is quite large as well. And the cart should achieve a maximum allowable speed of 1.2 meters per second during its motion. Right, so with that being said, we can then follow the optimization procedure again. So just before I move over to the DAP BC Dynamic Q workbench, you will see that all of the steps are given over here, as well as screenshots of where we made the amendments. And then the final design graphical results are also given here at the end, which we will look at. So I'm just going to switch over to DAP BC now. Right, so the DAP BC Dynamic Q Hybrid Workbench, we're working with revision 1, which was updated to ensure that we have that integration between the dynamic analyzer and the optimizer. Right, so what we can first start off with is we can go to the dap.m file over here. And what you'll notice, it still says PR_D over here. So if you recall correctly from the lecture mind map, we said that we're going to work with cart D. So we can just update this to say cart_D. Right, so in addition to that, all of these things are fine. We get our model input files from the models folder. We include global as well. So once again, we can just make sure that under formulation, some files include global, that we have xdap defined over there. So that is fine. In addition to that, we still use an initial condition correction for all of our iterations. So answer equal to y is fine over here. In addition to that, we also need to update our final time now. So we just changed this to 6 seconds. And then our DT, our reporting time step is quite fine over here. So we just want to update that to the 0.1 seconds that we specified for this problem as well. Right, so with all of that done, we basically updated our dap.m file. So that is fine. So we did make sure that under include global, we also have xdap defined over there. So now we just need to define our design variables in terms of their indexes or indices. So then we can head straight to models over here. So we head to card D and we go to, I'm going to open up in forces. So you'll notice the two forces that we have over here, F1 is weight, so we don't want to change anything over there, and F2 is the user force, so this was the aerodynamic force that we defined over here. So we can actually head to user force over here. So this is what the user keyword refers to. Right, so heading to user force, we just go in and we see over here we now have our motor torque, and we also have our aerodynamic resistive force over here. Right, so with that in mind, we now define each of our design variables. So we said that the maximum torque is going to be one of our design variables. So we can actually go to Tmax over here and we define that as x1. So in other words, xdap1 because we're working in the dap.bc files. So xdap bracket 1. And then also the aerodynamic resistive force. We said over here we want to change the aerodynamic damping coefficient. So this is going to be xdap2. We're going to define this as our second design variable over there. So our torque, as you know, is going to be in Newton meters. Our aerodynamic damp coefficient, because it's multiplied by the velocity, your aerodynamic damp coefficient is going to be in Newton seconds per meter. Right. So then we've updated the user force as well, so that is fine. Then just referring back over here, we can go and we can say, okay, so we've now updated all of these things. Now we just need to define our objective function and also our equality constraint value. So remember, we're working with the speed of the card. These values we only get out after the post-processing has been done. So we can head down to post.m and we can just take out these two lines. And we can say, so for our objective function, we need to maximize the acceleration. So the acceleration of card 1 is going to be in the x direction, so we only need to consider that component. So we're simply going to say that the max acceleration is equal to, let me just zoom in over here. Yeah, so the maximum acceleration is then going to be the maximum value, and we're going to use the magnitude of the acceleration. So we're just going to say absolute, and for BD, we want to look at all of them for body 1 in the one direction, which is in the x direction. Right, so then we just close our brackets. So that's the objective function now defined. And the other one that we're also going to work with is the maximum speed of the system. So, or the card body rather. So we can simply say over here max underscore speed. And we can once again use the magnitude. So we're going to say the maximum absolute RD, which refers to the speed. We consider all of the values of body 1 in the one direction, the x direction. Right, so now we've, yes.
I have a question regarding the user force.
Yes. Yes.
They have said that it don't depend on the orientation of body too.
Yes. Yeah. So.
So I want to know that in the real motor, like electric motor, is the torque always constant or it depends on the orientation?
So the torque, yeah. So if you look at the equation, I think your torque will depend. Yeah, it will most likely depend something like we have over here. So the motor torque, as you can see over here, was calculated from the maximum torque, and it depends on. Okay, so omega over here is actually the determining factor. So omega is not your angular displacement, your angular speed. So that is going to influence your motor torque value. Yes. So this is just basically an equation that was implemented. There are most likely other models that you can also use for the motor torque.
Because usually the motor has a constant speed. So
Yes.
it means that value, the motor usually wants the constant speed. So
Yes.
that value
Yeah.
doesn't change.
Yeah. So like you said, if you have a constant speed, omega is going to remain the same. Which means this entire relation over here is going to remain the same. But if you have some sort of an angular acceleration, then your speed is going to change, so your motor torque is also going to change. Yeah. Right. Okay, so just moving back to the post processor. So we've now defined our maximum acceleration, our maximum speed. So now we can actually head over to the minimizer inputs.m file. So remember, this is the transition file, the file that we use to obtain all of the data from our DAP-BC workbench and just give it as input to the dynamic queue optimizer. Right, so we don't need to change this add path. The include global is fine. xDAP equal to value is fine. DAP post runs, which is also fine. So now we just need to update the objective function. So remember, we are busy with a maximization. So in order to just change it to a minimization problem, we once again just multiply by -1. So I can just say -1 times, if I go back to post, the value that I'm interested in for my objective function is this max ACC. So I can just update that over here and I can say max ACC. Right, and for the equality constraint as well, we define it under minimizer inputs because our maximum speed is only determined after the iterative process. So we don't have an explicit relation in terms of the design variables for the maximum speed. So all that we're going to say over here is max speed. And if we look at the equality that we need to use, we can just hit back over here. So we say that the card should achieve a maximum allowable speed of 1.2 meters per second. So that means that my speed should be equal to 1.2 meters per second at the end. So I'm just going to say max speed minus 1.2. Right, so then my objective function and my constraints are defined. So the next step is then to basically just call this function under the FCH file. So I just go to the dynamic queue subfolder, fch.m. And if I look over here, I can see that indeed it gets f and h1 from the minimizer inputs x. The only thing that I want to change is now I don't have this h2, so this was for the previous example that we did. So we can basically remove that, and then we have our objective function defined and our equality constraint defined as well. Right, so then just to make sure under the grad FCH file as well that I'm still using my forward difference method, I can see over here that the step size is still 1.e minus 8 basically. So this is just a different way to write it once again. Just zoom in. So yes, it still uses the forward difference method to determine all of my gradients, so that's also fine. So we're going to look at the sensitivity analysis a bit later. Like we said, this is The sensitivity analysis is a bit out of scope for this module, but we can still look at what you would expect once you run the sensitivity analysis. So I'll just give you a breakdown of how that also looks if you want to use it in future. Right, so with grad FCH updated, the next step is then to head to our optimization.m file. And this is where we're going to change all of the starting points, the lower and the upper bounds, all those kind of things. Right, so if we just refer back, we'll see over here the torque should not exceed 50 Newton meters. So clearly we've defined some sort of an upper bound on X1. So if you remember correctly, X1 is the maximum torque. So we can actually start over here with the value, let's say 20 Newton meters. I'm just going to remove X3 and X4 as well. And then X2 would be the, so that would be the aerodynamic drag coefficient. So we can maybe use, let's say 10 Newton seconds per meter over there for that one. This X0 just combines all of your starting points into a list. So we just want to remove X3 and X4 because we're only working with two design variables. So for the upper bound, X1 must now be smaller than or equal to 50. So we simply update this and make it 50.0. Remove that. And additionally, we don't have any lower or upper bounds on our second design variable, so that's fine. That will basically sort itself out because of this 1.2 meters per second. Right, so we can then remove low as well. And then we just go over our DIN-Q input as well. So we do have our starting. We have the lower bounds going in. We don't have any upper bounds, so we can just leave this as an open list. I'm going to leave the move limit as 1 for the moment. And then we can also use over here, let's use the default of 10 to the power of minus 5. And we can also use 10 to the power of minus 8 as the standard on the function values as well, the convergence tolerance. Yes.
The X is the one that got there in the upper bound.
Yes.
That's the upper bound on the first design variable.
Yes. So the for the upper and the lower bounds, whenever you define them in a list, the first entry or the first column always denotes the design variable that you're working with, and the second column denotes the value that you assign as the lower or the upper bound. Right. Okay. Yes. 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 So so basically we only have a, oh sorry, yes, you're right. So this should be an empty list, and then we have an upper bound over here, so that should be up. Right. No lower bound. No, sorry, it was actually the upper bound that I referred to. So yeah, so you only have an upper bound, no lower bound, because we'll see from the example that we expect that a larger torque will cause a larger angular acceleration. So yes.
You don't have a lower bound or upper bound for like variable 2.
No, so that one will also sort itself out with regards to, no, not necessarily. So it's usually a good idea to start with a few equality constraints, and then if you see something that tends to infinity or does something weird like that, then you can start bounce to that. Yeah. Yes. Yes. Yeah. So the variable index. So in this case, because X1 is our maximum torque, so we say the maximum torque should be smaller than or equal to 50 Newton meters. So we say X1 is the variable that should be smaller than or equal to 50. Right. So with, yes. No. So we'll see now from the example that it's not necessary because we specified an equality constraint that is related to the speed. We don't need to define a lower bound on either the aerodynamic drag coefficient or on the maximum torque. So you'll notice with the torque, what we expect is that if we increase the torque, the acceleration of the system is also going to increase. So remember torque is equal to J theta double dot. So if I increase my torque, theta double dot is going to increase, which means the wheels are going to basically rotate faster, and the kart is going to move faster or accelerate faster. So we're going to see this now from the example as well. Yes.
Sorry, so you say every start with no constraints, so many things you add, so
Yes.
how would the optimizer run if it doesn't converge in a solution? Will it just stop?
Yes. Yeah, so we're basically going to look at an example of that as well. I'm actually going to change, I think, for the for the equality constraints. I'll just change that max speed value to something like 2 meters per second. So what you'll see is the dynamic queue optimizer is basically going to hang. So you're going to have a perceptible difference in the computation time between 2 consecutive iterations. But yeah, in general, you can still define bounds or inequality and equality constraints starting off. It's just you don't want to over-constrain your system either. So rather be mindful of your constraints and use them in a way that makes sense, and then they'll sort each other. Yeah. Yes.
Yeah, if we were interested in, let's say, body one, if we want to maximize or minimize something,
Yes.
how would we define the moment of inertia of that body that is harmonic translation?
So you're referring to the mass moment of inertia, or the yeah. So yes, yeah. So in this case, we didn't make any of the design variables a factor of the mass or the geometry of the system. So you'll either find the value of the mass moment of inertia like analytically. So you'll probably have like a sort of an equation that describes J in terms of the mass and the length, or the geometry. Otherwise, you'll just find it like from a specification or something. But in this case, we don't need to worry about that. So the geometry and the mass properties in this case are constant. So we don't need to change any of that for this optimization. Yeah. Right. So any other questions before we move on? Okay. Right, so with all of those changes now made, now we can simply go to our command window and we execute optimization. So I'm going to run it. It should run relatively fast. But what you'll notice is that for each iteration, there are quite small changes in the values for x1 and x2. So we can clearly see that the value of the acceleration is being minimized, or the negative of the acceleration is being minimized. We do also see clear convergence over here. So we can see it goes from -1 or 10 to the power of -1 to 10 to the power of -2. And these values also decrease. So yeah, as you can see over here, the values are increasing or decreasing for x1 and x2 quite slow. So I'm not going to run it for all of them because we used quite a fine convergence tolerance. But one of the main reasons for this is because of how we defined our move limit. So remember that we now kept it at 1, which is the default value as well. However, if we consider the values of our torque, for example, we can see that the upper bound is 50, and we start off with around 20. And this value can go even smaller. It can go from 0 to 50 or something like that. So we have quite a large variable range that we're looking at. We can go anywhere from 0 to 50 or 20 to 50 or something like that. So if we refer back to the general procedure, yes.
In the first lecture,
Yes.
they don't something to the power.
Yes.
-5.
Yeah.
So here we have like minus.
Yeah. So yeah. So the convergence tolerance that we specify over here. So this is on X norm. This is the one that we keep 10 to the power of minus 5. So you can make this 10 to the power of minus 8 or 10 to the power of minus 3, depending on what level of accuracy you want.
But the result
Yes.
is to the power of minus.
Sorry, which one is that?
The result
Yes.
that we have, the norm is not.
Yeah, so I just stopped it now. So I manually Control C and then you stop the program. If I were to run this thing for, let's say, 20, 25 iterations, even more, it would have went to the 10 to the power of minus 5 value at the end. So I'm just going to, for the sake of time, not going to execute all of the iterations. It will take a while. It's just basically to show that for your move limit, which we now assign as 1, the convergence behavior is quite slow. So you can see over here it starts -1, then it goes -2, and then it basically stays at -2. And then it's going to go to -3, stay there for until it reaches -4, -5. So it's going to take quite a while to converge on the tolerance that we want. So what I can actually do to accelerate this system is I can change my move limit value. So referring back to the procedure that Dr. Alex Hay covered in his code addendum, he basically says that your move limit should be more or less the same order of magnitude as the radius of region of interest that we're looking at. So to calculate that, we say it should be the square root of the number of design variables that you have. In this case, we have 2 design variables multiplied by the max variable range. So in our example, that would be, let's say, 50 Newton meters, for example. Right, so we get it at around 70. So if I were to now go and change this value to 70, and I ran the optimization again, we should expect to see that it now converges quite quickly, or at least faster, and we'll see more clear differences between these X norms as they decrease. So right, so here we can already see it now jumped from 10 to the power of -1 to 10 to the power of -3. Now it just went up again. So basically you'll see that it will converge after, let's see, after 8 iterations. So it converged on the function value in this case. So it found that x1 is now equal to 50 Newton meters. So in other words, at that upper bound that we specified. And x2, which is our aerodynamic damping coefficient, converged at 15.6 Newton seconds per meter. So this value didn't tend to infinity or do anything weird like that. So this shows that we didn't really need a lower or upper bound on the x2 variable. So just to also look at our constraint values, we can see over here our equality constraint is 10 to the power of -8. So this is essentially 0, which is basically what we expect for this problem. And then the upper constraint that we define on x1, so it should be smaller than or equal to 0. This one is also 10 to the power of -8, so also 0, which is fine. And the total optimization runtime is 1 minute, which is quite impressive for the optimization in this case. Yes. So that was the DML, so the move limit over here. So just after you've defined your upper boundary condition, you can define the move limit over here. The move limit. Yes. Yeah, so the move limit, yes.
I want you to ask the third question
Yes.
about the tolerance.
Yes.
The last one was 10 to the power of -1.
Yes.
So it does not affect
Yeah.
the tolerance input.
So in this case, if we look at the X norm, it didn't converge on that one. So this one is still 10 to the power of -1. But if we look at this RFD value, it's 10 to the power of -9 at the end. So what your dynamic queue optimizer basically does is you give it two convergence tolerances to input. The norm, convergence tolerance on the design variables, and the second one is the convergence tolerance on your function value. And what the optimization does is, if either of those are met, then it terminates the optimization. So in this case, although it didn't converge on the X tolerance, it did converge on the function value tolerance. So if we look over here, this function value tolerance over here that it converged on. And basically the way in which it calculates this is it says, take the best value for your objective function that you found so far. In this case, if we compare them, it's this value over here, so -4.03, and then take the value for your last iteration that you now looked at, and compare that to that value. And if that difference between those values is smaller than 10 to the power of -9, then it converges. Then it says, okay, so this is the best objective function value that you're going to get out, subject to your constraints and everything. Right, so yeah, so basically the crux of the matter is it didn't converge on your X values, but it did converge on your function values. So it's still a converged solution, and it still attains all of the equality and inequality constraints that we defined. Right. So we can just once again type in X just to see what the values is. You can also say format long if you're interested in more decimal places and everything. So the values for X, and then F at the end. So this is the objective function value, -4.03225. So of course, to get the maximum acceleration, you're just going to multiply by -1 again to change it back to your acceleration interpretation. Right, so now that we have all of these values, we can, yes?
Yeah, we can just have only one objective function.
Yes. Yeah, so dynamic queue is a single objective optimizer. If you're interested in multi-objective optimization studies, so let's say you want to maximize your acceleration, but you also want to maximize your speed, something like that, then you'll look at those multi-objective optimization techniques. So I think one of them is something like a Pareto optimization that you can do. Something else is also global optimization techniques also make use of multi-objective optimizations, and then there are a few gradient-based optimizers that also include multi-objective optimizations.
Because I find that last time when you make you use like H1 and H2.
Yeah.
I find that you can also play to.
Yes. Yeah. So you can definitely reorganize or reorder your problem to do like maximization on one parameter, minimization on another parameter. For the case of these studies that we're looking at, it's still basically just to introduce the idea of how optimization would be integrated with GAP-BC. Another example, if I'm now talking about my own project as well, something would be like changing the design variables based on the geometry of the Stewart platform. So you might want to change the distance between two legs, but you also want to maximize the acceleration that your platform is going to achieve. So you want to minimize your actuated forces, but you also want to maximize the acceleration. So that's an example of a multi-objective optimization. So something like a Pareto optimization. What it basically does is it does a bunch of different optimizations, and for each optimization you get certain design variables out which either maximize or minimize some of the variables out. So yeah, it's definitely if you find in your own projects that that is something that you're interested in, there's quite a lot of information with regards to multi-objective optimization. So yeah, I think MATLAB itself also includes quite a few workbenches that, or modules that cover that. So, yeah. Right, so moving on. So we can now basically go and look at our outputs that we're going to get from DAP-BC. So we've now obtained the optimum solutions. Now we just want to see graphically what is the effect going to be within the dynamic analysis. So because we're still working with a sort of a parametric model, we can't just clear all, close all, and just type in DAP. We need to first define these variables, and I'm going to show you why. So we're just going to copy those things. Okay, so I'm just first going to say clear all, close all. Right, so if I try to run DAP now, it's basically going to give me this error, which says xDAP1 is out of bound. So this is mainly because I now don't have any value specified for xDAP. So now I first have to go and re-specify it based on those optimum design results. So if, for example, you accidentally cleared your command window or something, and you want to find those values, you can just head over here to dynamicq.out. So this is in the main folder. So don't pay attention to this dynamicq.out file over here. This one is local to dynamicq. So you want to always work with the files in your main folder when it comes to these output files. So we can go to dynamicq.out, and over here you will see all of the results are given for each iteration, and also the final equality and boundary condition values that you got out. Right, so in my case, I now just copied the values over. So I'm just going to say xDAP, and I'm going to combine those values in a list. Right, so now I can say DAP post. Right, so this first this warning that it basically gives is just because we didn't now say include global first. We first defined xDAP and then we say include global. So whenever you do a minimization or something, you usually first say include global and then you define the like xDAP values. So this is just, we don't need to worry about this because we're just running it once and we want to check what the plots look like. Right, so then we can go ahead and, so I'm just going to type this out. So I did type it in before. So if you type something like this in and you just want to go back, you can just hit the up arrow and then it will cycle through all of your figures that you plotted in the command window before. Right, so in this case, I first plotted the acceleration, so the x acceleration of the card body. So if we look at those, right, so we can basically see that the value over here is at the maximum. So at time 0, it has the maximum acceleration that it achieved. And then from there, it basically goes down and then it reaches a constant velocity, so your acceleration just stays at 0 over there. Right, so this is what the maximized acceleration curve looks like. The next one that I can plot is also the angular acceleration of, so this is wheel 2, so this is the rear wheel that we're looking at now. We just want to see how its angular acceleration changes as well with respect to all of these properties. And if we look at that, we can see that it starts off at around minus 40 radians per second square, and then it also reaches a constant speed, so that's also within expectations. And then lastly, we can also look at whether the speed was indeed satisfied according to that 1.2 meters per second case that we looked at. And we can see over here, once it reaches the constant speed, it remains over here at 1.2 meters per second. Right, so with regards to the graphical outputs, we sort of validated everything that we got out. So a few questions that we might want to ask ourselves is, what happens if I have sort of an infeasible constraint that I specify. So I'm going to keep this value as 70 for my move limit, but I'm going to head to my minimizer input, and I'm going to change this value to 2.0. So from basically just from manually varying the values, I found that the maximum speed doesn't go higher than 1.25 meters per second for this problem and for these constraints and stuff. So 2 meters per second is definitely not going to be attainable for this problem. So we just want to see how the dynamic queue optimization is going to act if I do that. We can just type in optimization.
The drag coefficient.
Yes.
Making that design variable, obviously that implies that you change the shape of the part.
Yes. So I think a more clear study would be to also then change the geometry and stuff. But of course, so that would then influence the call it the mass moment of inertia. In our case, we just assume that the drag coefficient is the one that we want to work with. So we assume that it's going to keep the same mass moment of inertia and all of those things. But yeah.
I wonder also, it will be quite interesting, I think, to investigate the maximum distance the car can drive in 6 seconds.
Yes, definitely. So yeah, so that would then be just I think updating it with regards to the displacement. But yeah, I think that would be a good study as well to do. So there's quite a lot of, I think, maximization and minimization problems that one can actually get out of these application examples. So yeah, it's definitely worth investigating something like that as well. Yes. Right, so we can see over here it runs quite for quite a while. So it's basically struggling to attain that equality constraint value. So we can see the smallest that we got over here is 10 to the power of -5 on the yeah. So on the X norm. But a problem that we see now basically for all of them is that the drag coefficient is negative. So this is one of the problems that you'll most likely come across if you have infeasible equality constraints. So I just stopped it now. It's basically going to continue on and on. So at the end, it's just going to optimize, or it's going to terminate on the maximum number of iterations, and the values that you're going to get out is not going to make sense. It's going to be impractical because your X2 value, your aerodynamic drag coefficient, is now negative. You can't have a negative value, you expect it to be positive. So I can go ahead and specify that X2 must be greater than or equal to 0. However, looking at the problem, it shouldn't be an issue that I have to define those type of boundary conditions. We now see from the previous case where we use 1.2 meters per second that it actually works without any lower or upper bound on that system. So it's just being more mindful whenever we define these sort of values for our equality constraints. Right. So any questions so far? Yes.
Yeah, I have a question, but could you quickly sum the car? Because I have a question regarding the action force.
Yes. Okay. Let's see. So just running it with the.
So we can call it LAM.
Okay.
After running.
Okay. Right, so let me just check over here as well what the variables are. So you said N. Oh, okay. No. Okay. Right. Yes.
Because we have two joints,
Yes.
so we're supposed to have two reaction forces
Yes.
that will make four
Yes.
reaction forces. Maybe we can double click here. Yeah.
Oh, over here. Okay.
So in this case, we don't have four
Yes.
reaction forces.
So
We have two joints.
yes.
We're supposed to have two reaction forces. So we have more than four.
Yeah. So if I'm not mistaken, I think for this problem, you actually have more joints because you also have those disk. Yeah. So you also define these. So you define the revolute joints, which is basically between the card body and the wheel. But then on the wheel, because it's a disk, you want that no slip condition as well. So you're actually going to have more Lagrange multipliers which correspond to reaction forces. Because that disk corresponds to the reaction forces at the point of contact. So in this case, because we have a total of four, so you'll see over here we have four joints. If we go back to, I'll close it now. We go back over here, we see we have eight Lagrange multipliers over here. So it's 4 times 2 is 8. So there's two Lagrange multipliers or reaction forces associated with each of your joints. Yeah.
So this should have only one reaction force.
No, I think it has 2. Yeah. Yes. So yeah, it's because it's your upward force, and then I think there's also the frictional force, if I'm not mistaken. Yeah. So you have an X and a Y reaction force. Yes. Yeah. Right. So any further questions? Okay, perfect. Right. So now we've basically investigated how the move limit influences your convergence behavior. We've also seen we've also seen what happens when we are not quite mindful with our equality constraints, when we have sort of infeasible equality constraints. So the other thing that I just want to shift your attention to is then the sensitivity analysis. So before I jump back to the mind map, I'm just going to first show how we can implement the sensitivity analysis. Right, so you can just go to the sensitivity analysis.m script over here at the bottom. All right, so typically just running through this, there are a few things that we will note. So firstly, I defined an X as basically an X point over here. So this is generally the starting point whenever you do your optimization. So in our case, we used, I think it was 20.0 and 10.0. So this is 20 Newton meters and the 10 Newton seconds per meter value that we also used. Okay, so then N is simply the length or the number of design variables that you have. This weight bar is just to show the progress of the sensitivity analysis. Right, so then I created a for loop over here, and I set counter equal to 1. Epsilon value is now 10 to the power of minus 12. So epsilon value corresponds to the step size that we use. So remember, up to now we've used for our grad FCH file, we've used 10 to the power of minus 8. So now I ask, well, what will happen if I vary that step size from 10 to the power of minus 12 up to 10 to the power of minus 3? Okay, so just going into the loop then, this delta x that I define over here is just to initialize the basically the change in the x variables. Right, so then I do sort of a forward difference method with regards to my objective function. So I just have to change this. So if you look over here, I can just say fx and h1, because remember I'm only working with an objective function and one equality constraint. This max force funct we can also change to minimize your input, since that is the transition file that we're working with now. Right, so then after I've calculated these objective function and equality constraint values at that point. Now I want to calculate it just to the right of that point. So I'm going to take whatever the x variable is. In this case, yeah, so we basically take x plus delta x, and then we calculate f dx, and we're also going to calculate h1 dx. So h1 dx, which is once again minimizer inputs. Right, then I just say f is then equal to f dx minus fx. So this is where the forward difference method comes in, and I divide it by that step size. And then I just add all of those things to a list, and I can go and plot these things. So I'm just going to change, see, figure 3 and 4. So I can make this 1, and I'm just going to change this as well. So this is f list, so I also want to create a list for my quality constraint values. I'm just going to do that. Do this. So basically just copying it over for the equality constraint as well. Right, so then this one is just 1. So then the sensitivity analysis will execute, so we can just basically check the, let's see, h1x. So I think while it's running, we expect to get some sort of a relation between our objective function or our equality constraint and the step size. So once it's done, I'll just show you how those graphs look. Yes. Yes, so I think the documentation is just with regards to that dynamic queue general procedure that was given as an addendum. So I think it is also in the mind map, but because it was standalone, it doesn't really give you a lot of information of how to combine it now with something else. But yeah, you can review the how can I say, the Word document that they used in the development of the dynamic queue. So that is in the lecture mind map, I think, as well. Yes, so you'll see under, I think it's heading 3, it says optimization examples, and then the first one gives you like a general procedure. So there's like a little Word icon that you can just go to. Awesome. Right, so let's just start with the objective function with respect to epsilon 1. Yeah, I just want to check if it's visible here as well. Okay, so basically starting with that one, we can see that if we go too small with our step sizes, then the values between two consecutive step sizes change quite drastically. So ideally what we want to do for a sensitivity analysis is we want to choose a step size that is on the constant line that we have over here. So that ensures that your optimization has stability within it. So for example, in this case, it's 10, we choose 10 to the power of minus 8, which is fine. If we look at some of the other graphs as well, so this is, I think this is actually the, let's see the equality constraint. So this basically shows that there is no variation of your so no variation of your objective function with respect to x2. So x2, which was the aerodynamic force, is mainly just due to or mainly just used to change the velocity so that we get that 1.2 meters per second out. Right, so in this case we can also choose 10 to the power of minus 8, clearly it's constant. Then for this one, which is now our equality constraints, we can see that for x1, 10 to the power of minus 8 is also fine. And then for the last one as well, the equality constraint based on x2, you can also see that 10 to the power of minus 8 is also more or less on that constant line. So 10 to the power of minus 8 is overall a good step size. So typically whenever you choose your step sizes, it's a good idea to stick between 10 to the power of minus 7 to 10 to the power of minus 9, but it will also depend on your sensitivity analysis. But yeah, like I said, that's basically just an addendum to what we're discussing. We won't expect you to do a sensitivity analysis for this module, but it's just good to take that into account as well. Right, so I think that is everything that we wanted to discuss over here. So I'm just going to jump back to the mind map. Right, so we've basically now run through the optimization procedure. So just a few results as well that I think need to show. So just with regards to the convergence history and all of those things, so we can sort of a spiked convergence over here. But we do see that the objective function clearly decreases over here. So we can see over here, this is the minimized acceleration that we're going to get out, so that's fine. With regards to our variable history as well, we can once again see that spiked behavior over there. So this one was, I believe this was over 4 iterations, so there were a few changes that I made to the convergence tolerances and stuff as well, so you're more than welcome to play around with that. This data that we use as input over here is given within the mind map as well, so you're more than welcome to reiterate on these examples. Right, so then with regards to the lower limit equality or the upper limit inequality constraints, and I think this was the equality constraint over here, we can see they are all either at 0 or below 0, so that is also fine. Right, and then the results that we got out, so this was different parameters that we used as input, but we still got the same optimum out over here, so that is fine. Right, so just looking at the final design results as well, I've just plotted that as well, so you're more than welcome to look at that as well. Okay, yeah, so that concludes the card subjected to an aerodynamic torque and load example. Right, so a few concluding remarks that we can basically look at based on these application examples. So the effectiveness of the dynamic queue optimizer, because it's integrated with the DAP-BC Workbench, its convergence behavior, the computation time, all of those kind of things are going to depend on the complexity of the dynamic analysis that you're going to run. So that includes things like the number of design variables that you consider, the complexity of your objective function, the number of constraints and the complexity of these constraints, and also things like how fine is your reporting time step, how do you discretize your input parameters, and then whether there is noise or any discontinuities in your data as well. So it's important to notice that note that if you for example want to do post-processing, or you want to do an optimization on some sort of a parameter that is going to be discontinuous, it is going to affect the performance of your dynamic queue optimizer. So ideally, dynamic queue, because it's a gradient-based optimizer, it's more applicable to cases where you have sort of a smooth curve rather than discontinuities and spikes in your data, those kind of things. Right, then the optimizer itself will also have an effect on the solution times, and that is with regards to the convergence tolerances that we specify, the variable ranges, the move limits, which we also defined now, the type of finite difference approach that you also use. So remember, we said we're using the forward difference method now, but you can also use something like a central difference method. So it's important to note that for each iteration, your system will have to run, or your optimization will have to run n+1 times. So once for the design variables, and then it needs to go and calculate the gradient for each, well, basically for each of the design variables. Right, and then the last one that can also influence it is that step size that we looked at, and the parameter sensitivities, which we can determine from a sensitivity analysis. Right, so in general, it's always a good idea to strike a good balance between the accuracy that you want to get out and the performance of the optimizer. So of course, if you use very fine convergence tolerances, your system is simply going to take much longer to solve. Whereas if you relax your accuracy and your convergence tolerances a bit, you might get an answer that is just as feasible or just as useful as it would have been for a very accurate answer, but it's just going to take less number of convergence iterations. Right, so those are the main problems, or the main things to consider whenever doing this optimization and dynamic analysis. Right, so with regards to that, any last questions? Perfect. So if there are no other questions, that concludes the study theme. And yeah, so just like I said at the start as well, the lecture video for the first lecture will be posted within the next week or so you can expect that. And we will also make it available on YouTube and just update the class schedule so that you have access to that as well for the exams. Other than that, yeah, all the best for the assignment and for the exams. And yeah, thanks a lot.